Good morning all. Today we are going to study a very simple and a small topic, that is design of primary winding and secondary winding in transformer. If you know the value of voltage per turn, which is usually indicated by the symbol ET, then you can easily find the values of primary number of turns and secondary number of turns by dividing the voltage at the primary side and the terminal voltage at the secondary side with ET. As a standard practice, the number of turns in the primary side, that is TP, is determined by adjusting the value of ET so as to get the value of TP as an integer. This is actually a standard practice. Usually, the number of turns in the primary side is determined after adjusting the value of ET so as to ensure that the TP is an integer one. So once after the value of TP is determined, that is the number of turns in the primary winding is determined, you can easily find the number of turns in the secondary winding by using the standard relation. This relation you are quite familiar with. You have studied them in your electrical machines first classes. That is E2 by E1 is equal to N2 by N1. There we have represented the number of turns in the secondary as N2 and number of turns in the primary as N1. That same relation is being used here. So T high voltage is equal to, this will be N2. The value of N2 can be easily determined by E2 by E1 or V2 by V1. V2 is actually V high voltage divided by V low voltage into N1. N1 is number of turns in low voltage side. We have already determined the relation of ET in our output equation derivation video session. There we have learned the value or the relation for ET as ET is equal to K into square root of Q. Otherwise also, this value of ET, that is EMF per turn, remains same both in the case of primary winding as well as secondary winding. Its value in the case of transformer is 4.445 M into F. Next, let's determine the values of primary current and secondary current. Only if we know the values of primary current and secondary current, with the help of their current densities, we will be able to calculate their cross-sectional areas. The current which is flowing through the primary winding can be easily determined by using the standard relation. As you know, the transformer's power rating is always said to be in kVA. kVA per phase can be written as Vp Ip into 10 raised to minus 3. From that relation, we can easily determine the value of primary current as kVA per phase into 10 raised to 3 divided by V phase. If you are aware about the value of primary current, you can easily determine the secondary current with the help of transformation ratio. As you all very well know that the relation V2 divided by V1 is equal to N2 divided by N1 is equal to I1 divided by I2 is equal to K. So it's clear that the relation I2 by I1 will be giving you the value 1 by K. So this I2 is actually the secondary current and I1 will be the primary current. So we can write I2 divided by I1 as Is divided by Ip is equal to 1 by K, which is written as V primary divided by V secondary. All these relations associated with the transformation ratio of transformer, you have already studied them in your electrical machine session. Once after identifying the values of primary current and secondary current, we have to choose a suitable value for current density in order to find the correct area of conductors in both primary and secondary windings. As you all know, the standard relation for current density is current per unit area. So if you are choosing a very large value of current density, that means a large amount of current will be flowing through a very small cross-sectional area. This will definitely cause the temperature rise in the winding to become very excessive, which will further cause injuries to the insulation provided. Therefore, the values of current density is chosen considering the heat generated in the machine and the prevailed ventilation or the cooling conditions which are available in the machine. The machine means the transformer one. The different values of current density for different types of transformers are given here very clearly. In the case of distribution small and medium power transformers which are self-oil cooled type. As I have told, this cooling type, which type of cooling is being provided, also has a determining factor or has a great influence on the selection of the value of current density. And the power rating is up to 50 kVA. We will be using the current density of 1.1 to 2.3 ampere per millimeter square. Next, large power transformer. It's a self-cooled one or air blast cooled one. The value of current density chosen here is 2.2 to 3.2 ampere per millimeter square. Next is another type with forced circulation of oil or water cooling. Here we will be using 5.4 to 6.2 ampere per millimeter square. So from this values, it's very clear that they have great dependency on the cooling type which is being provided to the transformer. Next, let's see the condition for minimum copper loss. As we know, the area, that is the cross-sectional area of primary winding, can be found out from the relation of current density and current by using this equation, that is AP is equal to IP by del. Similarly, the cross-sectional area of secondary winding can be determined by using this relation, AS is equal to IS divided by del. The volume of primary conductor is indicated as UP and the volume of secondary conductor is indicated as US. Therefore, the total volume is UT and it remains a constant. It is actually the sum of volume of conductors in primary winding and the volume of conductors in secondary winding. The copper loss in the primary side can be written as IP square R. In this relation, the copper loss in primary side can be written as IP square R. In this relation, this IP can be substituted as del AP. When you are substituting IP as del AP, the relation gets further modified into the form del AP the whole square into R. And for that value of R, you have to substitute in terms of rho L by A. So the relation for R in the case of primary winding is rho LP divided by AP. So now the relation of this I square R in the primary side is modified into the form del AP the whole square into rho LP by AP. On further simplifying it, you will be able to cancel the AP term at the denominator as well as on AP term in the numerator. Finally, you will be left with a del P square term, AP into LP into rho. This AP into LP, that is actually the cross-sectional area into length of the conductor, can be written as the volume on the primary side, which is represented by UP. Finally, you will be getting the relation as rho del P square UP. All of you must try writing down this relation in your notebook. Next, similarly, we are finding the value of this copper loss in secondary. In the same way, we will be able to determine it as rho del S square US. Instead of US, we can substitute it as UT minus UP. Therefore, the total copper loss both in the primary side as well as in the secondary side can be written by adding these two terms. And taking rho common from both these terms, the relation becomes like this. In this relation of total copper loss, this rho, del S, del P and UT remains constant. Therefore, in order to find the condition for minimum value of this, we have to find the first derivative of this particular relation with respect to UP. UP is actually the volume of conductors in primary side. So while finding that, we will be able to get the relation like this. As all of you know that the condition for maximum and minimum is we have to take its first derivative and equate it to 0. So I am equating this term to 0. From here I will be able to obtain that the condition for minimum copper loss is the current density in the primary side and the current density in the secondary side. Both must be one and the same. Now let's see the selection of different types of windings in transformer. Usually the high voltage windings are provided with cylindrical, crossover or continuous disc type winding. And in the case of low voltage windings, we will be providing either cylindrical winding or helical winding. You don't have to study about them in detail, you just need to know about them. When or for all voltage ratings we will be using this type of windings, that is also given here. Similarly, these types of windings are used for watt ratings, that is also mentioned here. Just need to know about them, that's all. Now let's see two numerical problems based on the selection of this transformer primary winding turns and secondary winding turns. In this first problem you are asked to find the main dimensions and winding details. The transformer given here is actually 100 kVA, 2000 bar 400 volt 50 hertz single phase shell type. It's actually a shell type transformer. EMF per turns value is given 10 volt, flux density, the ratio of window height to window width and ratio of core depth to width. All these parameters which are associated with overall dimensions are given. So I am not going into the details of this solution of the overall dimensions of this transformer. I will be just explaining to you the winding details, because till here we will be solving the problem just like how we have solved the problems in the topic overall dimensions of transformer. So let's find out the winding details. So in the winding details you have to find the primary turns, secondary turns, the current which is flowing through the primary winding, current which is flowing through the secondary winding, as well as cross-sectional area of both the windings. So since the EMF per turn is given as 10 volt, we can easily calculate the value of primary turns and secondary turns by dividing the primary side voltage and secondary side voltage with the EMF per turn. Similarly, we can identify the value of IP and IS from the relation of kVA, that is power. Once if we have find the value of IP by using this power relation, we can easily determine the value of IS by using the transformation ratio. It's clearly given that the current density of the conductors are 2 ampere per millimeter square. It's not specifically mentioned whether it's primary or secondary. That means it's both for primary and secondary, the current density remains the same, which is actually the condition for minimum copper loss. So by using this 2 ampere per millimeter square as current density and the values of the primary current as well as secondary current, we can easily determine the values of primary cross-sectional area as well as secondary cross-sectional area. Now moving to the second problem. Here also you are asked to find the number of turns and the cross-section of conductors. The transformer is 5 kVA, 11 kV bar 400 volt 50 hertz single phase core type distribution transformer. It's given very clearly. The current density is actually 1.4 ampere per millimeter square. It's also given. Usually in this type of problems, the determination of number of turns or the determination of the parameters associated with the winding is very easy to calculate. So even if you are skipping the main dimensions part, that is overall dimensions of the transformer, you shouldn't skip. But if in the worst case, if you are not getting any time or some problems are occurring, and if you are skipping the determination of overall dimensions of the transformer, then you can easily calculate this and fetch the marks of it. Now see, in this problem you are asked to find the number of turns. Just like in the previous case, we can easily find the number of turns by using the transformation ratio, that is number of turns in primary winding as well as number of turns in secondary winding. In this problem, the value of volt per turn is not given directly, so first you have to find that, then only you will be able to find the value of TP and TS. The EMF per turns relation is actually 4.44 F phi m, and this remains the same for both primary as well as secondary winding. So after making the suitable substitutions for F and phi m, but the problem with this is the value of phi m is not given directly, so you have to determine the value of phi m and you have to substitute it here. The value of Bm is given, and then you have to determine the value of AI. So there is no way for you to escape. You have to first determine the overall dimensions, then only you will be able to identify the value of AI. Only if the value of AI is determined in this problem, you will be able to calculate the value of phi m. Only if you know the value of phi m, you can easily find out the value of ET, which is EMF per turn. That seems to be 1.625 watts. With this, you can easily calculate the value of TP and TS. Once if the values of TP and TS is known, next let's determine the values of AP and AS. The value of AP and AS can be found out by using the standard relation, that is dividing the corresponding currents with the current density value. The corresponding currents can be determined by using the standard relation for power. There is a kVA rating is equal to voltage into current into 10 raised to minus 3. Using that relation, we will be able to find the value of AP as well as AS. With that, we are completing today's session. In the next session, we are going to study the design of transformers with cooling tubes. Thank you.